Let us now discuss one topic, that is vector differentiation. Actually, vector differentiation, it's a part of the topic vector calculus. This is an important component of mathematics or engineering mathematics. As all of us know that calculus deals with limits, continuity and differentiation, finds utility in many fields. So before we go for vector differentiation, let's recollect certain important aspects of the algebra of vectors. Let us initially recollect the definition of a vector. How do you define a vector? A vector is a quantity having both magnitude and direction. What notation we follow to write a vector? We can write A bar, AB bar, or when we want to show in a diagram, we use a directed line segment to represent a vector. Can we have an example for it? Let A be a point in space and O be the origin. Then the line segment joining origin to A will define a vector which we call as the position vector of the point. What are the examples for vectors? Position vector of a point, velocity of a moving particle, acceleration of a moving particle, a force are examples of vectors or simple examples of vectors. Let us now have the representation of a vector. We will make use of usually 2 dimensions and 3 dimensions to represent vectors. So let us consider the representation of a vector in 2 dimensions. In 2 dimensions, a vector A bar is represented as A1 A bar plus A2 J bar. In this notation, A1 A2 are known as the components and I bar J bar are the unit vectors along the positive directions of the x-axis and y-axis. Usually, in the 2-dimensional coordinate system, we take x-axis and y-axis. We call one as the x-axis, another line, vertical line as the y-axis. So that is the 2-dimensional coordinate system. Of course, we can also make use of the polar coordinates for representation, but initially I am thinking of the Cartesian coordinate system. This is one representation. Another representation is A bar can also be written as magnitude of A bar into A cap, that is a unit vector lying in its direction. Then let us think of a vector in 3 dimensions. Suppose we consider a vector A bar in the 3-dimensional Cartesian coordinate system. Then A bar can be written as A1 A bar plus A2 J bar plus A3 K bar, where A1, A2, A3 are known as the components of the vector along the 3 coordinate axis directions or directions of the coordinate axis. I bar, J bar, K bar are unit vectors along the positive directions of x-axis, y-axis and z-axis. Let us recollect certain aspects. For example, dot product of vectors. We are not going to discuss addition, subtraction. We are directly going for dot product of 2 vectors. Suppose A bar, B bar are two vectors. Then how do we define their dot product or inner scalar product? Actually, when we consider 2 vectors, we can have 2 types of products. One is a dot product, another is a cross product, depending upon the result of the product. So initially, let us discuss the dot product. How do you define the dot product of 2 vectors, say A bar and B bar? We define it as magnitude of A bar into magnitude of B bar into cos theta. What is theta here? Theta is the angle between the 2 vectors. Can we have an alternative definition? Yes. If A bar is represented as A1 A bar plus A2 J bar plus A3 K bar, B bar is represented by B1 A bar plus B2 J bar plus B3 K bar, then A bar dot B bar is equal to A1 B1 plus A2 B2 plus A3 B3. What are the uses of this dot product? The uses of this dot product. One is we can find out the angle between two given non-zero vectors. Another one is we can find the projection of one vector in the direction of the other. The third one is we can find out the work done by a force in moving a particle along a straight line. Let us now discuss another type of product of vectors. Let us consider A bar and B bar. Their cross product, that means when the result is a vector quantity, is defined in two ways. A bar cross B bar is magnitude of A bar into magnitude of B bar into sin theta into n cap. What is theta here? Theta is the angle between the vectors. What is n cap? N cap is the unit vector perpendicular to the plane containing the two vectors. When the components are known, we can have an alternative definition. That means A bar cross B bar can be expressed in the form of a determinant, where in the first row we write the unit vectors I bar, J bar, K bar. Second row, the components of A bar, namely A1, A2, A3. Third row or third line, we write the components of B bar, B1, B2, B3. That means when A bar is A1 A bar plus A2 J bar plus A3 K bar, B bar is B1 A bar plus B2 J bar plus B3 K bar, then the cross product can be defined by means of this third order determinant. Then let us see the uses of the cross product of two vectors. One is we can find out the angle between two non-zero vectors. We can find out the vector area of a parallelogram or a triangle whose coterminous edges are given by A bar and B bar. We can also have what is the vector perpendicular to or a unit vector perpendicular to the plane containing two given vectors. The dot product of two vectors will be 0 when either of the vectors is 0 or the angle between them is 90 degrees or pi by 2 radians. Similarly, cross product of two vectors is 0 when the vectors are parallel to one another or the vectors act along the same line. Let us recollect two more aspects related to the algebra of vectors. One is the scalar triple product of three vectors. Let A bar, B bar, C bar be three vectors. Then A bar dot B bar cross C bar or A bar cross B bar dot C bar is known as a scalar triple product. Why is this name? Because when we consider cross product of two vectors, the result is a vector quantity. When we take the dot product with another vector, the result will be a scalar quantity. Because the final result is a scalar quantity and the three vectors are involved, we call it as the scalar triple product. We see the expression for the scalar triple product when once the components of the vectors are known. Let A bar be represented by A1 A bar plus A2 J bar plus A3 K bar, B bar as B1 A bar plus B2 J bar plus B3 K bar, C bar as C1 A bar plus C2 J bar plus C3 K bar. Then the scalar triple product A bar dot B bar cross the C bar is given by the value of the determinant with elements row wise A1 A2 A3, B1 B2 B3, C1 C2 C3. What are the uses of this scalar triple product? We can find out the volume of a parallelepiped whose coterminous edges are A bar, B bar, C bar. We will also be able to know that the vectors are coplanar if their scalar triple product is equal to 0. Then another aspect we discuss is vector triple product. Vector triple product means we are considering product of three vectors. The result is also a vector quantity. So one way we can write is A bar cross B bar cross C bar. We can also write A bar cross B bar cross C bar. I am mentioning the first one, A bar cross B bar cross C bar. We can as well see that its expression is A bar dot C bar into B bar minus A bar dot B bar into C bar. So the immediate thing that comes to our notice is this gives a vector lying in the plane of B bar and C bar. It will be perpendicular to both A bar and also B bar cross C bar. With this background information, let us now go for vector differentiation. Vector differentiation, as we already recollected, calculus deals with limit, continuity and differentiation, integration and related aspects. Initially, we go for vector differentiation. When we want to discuss vector differentiation, let us think of the position vector of a particle. Earlier we have seen that the position vector of a particle is a vector quantity. Let us now think of a particle moving in space. If we consider its position vector, it will be a function of the time variable. Because the particle is moving, it will be at different positions at different instants of time. So its position vector will be a vector quantity. Then comes the question. When a particle is moving, it will have velocity, it will have acceleration. How to get velocity? We know that velocity means time rate of change of the position, and then acceleration means time rate of change of velocity. That means perhaps by considering derivatives of r bar and the velocity vector, we may be able to get velocity vector and acceleration vector. When the particle is moving, and if x, y, z are the coordinates of the moving particle, then r bar can be written as xi bar plus yj bar plus zk bar, or r bar as a function of t is equal to x a function of t into I bar plus y a function of t into j bar plus z a function of t into k bar. Its time rate is going to give the velocity vector, and the time rate of change of velocity is going to give the acceleration vector. So let us now know the basic or fundamental definition for derivative of a vector function of a scalar variable. Let f bar, a function of t, be a vector function like r bar of t. Then we provide the fundamental definition similar to that of a function of a real variable. How do you define d by dt of f bar? D by dt of f bar is equal to limit delta t tending to 0 or of f bar of t plus delta t minus f bar of t divided by delta t, provided the limit exists and of course it is unique. Then we know that a vector can have components. Suppose f bar of t is equal to f1 a function of t into I bar plus f2 a function of t into j bar plus f3 a function of t into k bar. Then df bar by dt can be written as df1 by dt into I bar plus df2 by dt into j bar plus df3 by dt into k bar. Now that we notice, if r bar t is the position vector of a moving particle, then one application of vector differentiation is we can find out the velocity vector and acceleration vector of a moving particle through differentiation. So, if v bar represents velocity vector and a bar represents acceleration vector, then v bar is equal to dr bar by dt and a bar is equal to dv bar by dt. So these are the velocity vector and acceleration vector of a particle moving in space.